Hi everybody, Dr. Pingle here. We are going to look at the creation of a digital terrain model using ArcGIS. We're going to use ArcMap 10.5 and we are going to build a digital terrain model, an estimate of sort of where the ground surface is based on LiDAR data for the Nechuza grasslands. So I pulled up the boundary of the Nechuza grasslands in OpenStreetMap so you can get a sense of where these are. For all I know, this is up on Google Maps as well, but if you ever wanted to download the boundary of this, it would certainly be easy to do this using OSM. We're not going to use that. We're not going to download the boundary file, but we are going to use these sort of references to try to help us download the right tiles. So to download the tiles, you've got a number of different options. So you can certainly go to the national map. In the state of Illinois, we've got the Illinois Height Modernization Project. So if you pull this up, it's a very up-to-date map that's sort of showing the current state of LiDAR data throughout the state. So you can see that there's a lot of stuff still missing. Some counties are better than others about sharing their data. If you go to the data tab over here, you can get a sense of what all of these are. Now, the Nechuza grasslands sort of is right in between two counties, Ogle and Lee counties. So you could go down to those counties directly and you could download the original LiDAR data. You could also get derivatives, and those would probably be fine. So some of those are probably going to include digital terrain models and whatnot. You can see that the clearinghouse, data clearinghouse, has a lot of different information, including TINs that have been created. But what we're interested in here are the LAS files. So LAS is the sort of original format point data for the LiDAR scans. This is as raw of data as you're ever likely to be working with. And so you could download the LAS files for Lee County, which is 31 gigabytes, and Ogle County, which is 34 gigabytes. But that's a lot of data, and so you might not necessarily want to do that. So instead, we'll show you a way that you can actually grab individual LAS tiles. So if you go to the viewer, you can see the same LiDAR data that's being served up via an Esri online map. So we can dive in here and sort of see and get a hold of this data. So we're going to zoom in. So here's Lee County right here. Here's Ogle County there. And as you kind of zoom in a little bit, we'll zoom out a little bit here so you can get a sense of where we are. But essentially, we're just going to use sort of feature matching to get a sense of the tiles that we're going to need. So here's the highway that kind of runs right near Dixon. So you can see it right here on the map. You can kind of also see this like little jog right along the river. So that's here. And if we zoom in, you can see that the Nechuza grasslands right here are sort of right along this little point here. So we're going to zoom in. We've also got road names over here. So this is West Stone Barn Road and East Stone Barn Road. If we zoom in here, you'll be able to see those as well. So here's West Stone Barn Road and East Stone Barn Road. And they're divided by South Loudon Road. So if you zoom in here, there's South Loudon Road showing up right here. You can see what looks like a digital terrain model underneath here. But essentially, the Nechuza grasslands, we could be a little picky about which tiles we download. But essentially what we want is kind of going over all the way to the end of West Stone Barn Road, all the way down to Naylor Road, and then back up. So this is the intersection of South Loudon Road and West Stone Barn Road. That's right here. So we're going to click on that as our first tile. We're going to try to get a rectangular piece here. And all that, it's very nice interface. You click on that, you'll get an LAS file that you can download. I've already downloaded all of these, so I'm not going to repeat the process. But essentially what you would do is you would create we'll call this one just Nechuza 2. And you would just start saving these into your directory. And your download speed is going to vary quite a bit based on your location. But the Illinois height modernization tends to be pretty fast. So you can kind of whip through these pretty quickly. I don't recommend downloading too many simultaneously. But in this case, essentially, we're going to be downloading 4 columns across. So 1, 2, 3, and 4, and then all the way kind of down to the end. So here's where Naylor Road meets Loudon Road. That's right here. So you may want to get sort of 1 row down just to make sure that, because the road kind of bends down. So maybe this row would be fine for the last row. So you can download all of those in between there. So 4 by 1, 2, 3, 4, 5, 6. So kind of a 4 by 6 tile. So 24 different tiles that you would download. So as I said, I've already done that. So here's the first 4 kind of coming in. I've already downloaded all of those. So let's take a look at that. So on disk, I've got these stored in the Nachusa folder, and here they all are. So there's the LAS files, and that's what you'd be downloading. There are these extra LASX files. You won't have those. In fact, let's just get rid of those. I've already sort of loaded some of these into Arc, and Arc has done a little pre-processing. So these are the files that you would have downloaded. So those 24 different tiles. In Arc, to bring these things in, there are a number of different ways, but what we're going to do is we'll search for LAS. So LAS is the file format. You can see back here, .las. So okay, so sorry about that. There's a video edit issue there, but so here are the 24 LAS files, and we are going to do search for LAS. So we're going to do create LAS dataset. And so this is going to be set to browse for files. You can change that if you want and browse for folders. Sometimes that's an easier way to do it. We'll just do files for now. And we are going to open our Nachusa folder and Control A to select all of these and hit open. So we're going to see this window populated with all of those 24 LAS files. This is kind of the key. So what we're outputting here is an output LAS dataset. Now this is going to, we're going to store this here to a directory. I like to work out of the temp directory for these videos. So we're going to store this as nachusa.lasd for LAS dataset. So the LAS dataset is actually just kind of a wrapper. Its job is to kind of facilitate access to all of these different LAS files. So it's not actually going to hold the data. It doesn't actually use up a lot of space or anything. But what it does do is just allow you to kind of interact with those. And actually, I'm going to, rather than storing this to the temp, I think what we'll do is we'll store this stuff to the desktop. So we'll go up to C. Actually, let's just do a quick connect here. So we'll connect right to the desktop here. And then that way it's going to be right at the main site. So Nachusa, and we're going to save this as nachusa.lasd, hit save. Now, we're not going to worry about any of this stuff right now. We're not even going to worry about the coordinate system. The coordinate system has been embedded into these LAS files. I'm going to compute the statistics. So those were those LASX auxiliary files that were in there when we started. Those didn't exist when I downloaded it, but I had already brought these in once. So we're going to run these statistics, and that's just going to make it a little easier to work with these. You don't need to do that, but if you can, it's often a good idea. And then I'm going to store the relative paths, and the reason for that is I want to be able to move this data around, and it's still going to be able to find all of this stuff. So we'll hit OK, and it's going to start creating that data set, and you're going to see it populate here in the window with 24 red boxes. So far this doesn't really look like much. This certainly isn't the LiDAR data that we were hoping for. But it actually is all here. It's just that each of these tiles is one of those 24 data sets. You can see over here in the upper left, we've got some point elevations here. So this is just a dot to represent each point in the LiDAR data set. And if we right click on Nachusa, we can actually get some more information about that data set. So you can get statistics about the LAS files. So you see that there are 24 in this data set. You can get a sense of the elevation range. This goes from 666, what are probably feet, to 907.8 feet. Often good to know things like what the coordinate system is. So you can see that this is a NAD 83 State Plane, Illinois West in feet. So that means that the X and Y coordinates are going to be in feet, which is going to be important later on. And then that also means that probably the elevations are going to be in feet as well. That's not always the case, but usually those two things go together. If it's going to be feet one way, it's going to be feet the other way. So we're dealing with elevations in feet and northings and eastings in feet. We've got a sense of the extent of this here. So the top, bottom, left, and right coordinates are given here. We'll look at this. We'll come back and look at this in a second. But the symbology is the other thing that I wanted to show you, which is here that we've got an LAS point elevation. We've got our symbol, so just a point symbol. This is corresponding to a range. So this is exactly like here. We're just using natural breaks. This is exactly like every other kind of a classification system. So you can come in here just like you can with other things and change this to equal interval if you like. You can change the number of classes to however many you want. And then that's going to show up over here. So obviously we still don't see any data yet. So to see that data, what we're going to need to do is zoom in. So there was a setting in here in the LAS data set for display. So you can look at some of this stuff, but basically what it's doing is it's going to act to hide a lot of those points when you are far away. And the reason for that is you don't want to display potentially tens of millions or even hundreds of millions of points on your screen. Your computer wouldn't like that. So it suppresses that stuff so that it doesn't get in the way. We're going to zoom out a little bit here. What I want to try to do is zoom out just enough so that you can start to see a bit of what's going on in the landscape without losing any of the data. So here you can start to get a sense here. So blue is relatively, in this case, high elevations. Probably it'd be a good idea to switch those. Red is relatively low elevation. So there's kind of a higher area over here and a lower area over here. And again, these are all point values. So if we zoom in here, what you start to see is these individual point returns. And this just gets back to a LiDAR data set is what's called a point cloud. And it's just, many, many, many points. In this case, we can take a look at the properties here. So what we're dealing with here is 20 million some points. And so just all over this area. So you can zoom in and you can start to see, they start to space out a little bit. We're going to go back and view that at its coarsest resolution. And just to take a look at the symbology here, this is where under display, we can do things like say always display the LAS file extents. We can label them, lots of different things that we can do here. So one of the things that we're likely to want to do is convert all of those points to a ground surface. So I'm going to zoom in here just one more time on this upper left tile. Now all of the stuff that you see is not the ground. Remember that LiDAR point returns are going to come off of all kinds of different objects, trees and buildings. And so if we want to build a DTM, a digital terrain model, what we really want to do is just build the ground surface. Now LiDAR point clouds often are pre-classified for you. So the contractors who gather this data will run it through some algorithms, and those algorithms will define what each of these things is. And those algorithms aren't perfect. And what they usually try to do is define some of this stuff. So this is under filter. We've got one unassigned ground points, noise points, key points, water, and rail. not a lot of things in this data set, and what kinds of different classes show up here. There are a lot more than this, but the classes that show up here are going to be a function of what is in your data and what those algorithms think is in your data. Those two don't always go the same. So, for instance, there's low-lying vegetation is one category. High vegetation like trees would be another. But if the algorithm doesn't detect those, or if it's not set up to detect those, then those aren't going to show up here, even though there's definitely trees and vegetation in here. But what we can do is we can filter based on a number of these different categories. So for instance, we can just look at the ground data, and if we hit apply, what you're going to see is a lot of those points going away. And if we zoom out here just a bit, we'll hit OK, and we'll zoom out so we get a better view of this. Again, I want to get close enough that we can see some of those points. There we go, and we'll center this a little bit. Okay, so what we're looking at here are only the ground points. If we go back into the properties and the filter, as I kind of turn on all of these, you can see that a lot of that stuff is gonna show up again. So the ground is going to be just a subset of these points. It's hopefully going to take off trees and buildings and all of that kind of thing. So this is our ground surface. So the next thing that we're going to want to do is build a DTM out of this. So we're going to look for DEM actually. So this is the one I'm looking for. So this is the LAS dataset to raster conversion tool. So this is going to take our input LiDAR dataset. We're going to output this. In this case, we'll put this back into the Nachusa folder that we've been working in. So we'll call this the Nachusa DTM. We'll hit, and actually we want to define this as a .tiff. The value field, you can actually make rasters. Remember, raster is just kind of a general term here, but we can make a raster of elevation, which is a DEM generally. We can make it of intensity values, so as those LiDAR points get reflected off of a thing, that it reflects with a certain strength. So we could make a map of that if we wanted to. Or sometimes a LiDAR point cloud will actually capture color values. So this is particularly true. Certain kinds of LiDAR units are paired with cameras. If you build a point cloud based off of photogrammetry, drone work, you might get an RGB value. But we're just going to use elevation here. So essentially what we have here is we've got two different ways to build a DTM. We can either do it by binning, in which case we're making a little grid all over this at a certain resolution. Or we can use triangulation to do it, where we're basically building a tin, triangulated irregular network with all of our points and using that to estimate the ground. And the reason that we have to do this is that you can see that point density varies quite a bit. So in this area right here, we're getting a lot of different points, but in this area over here, we have virtually none. So this is probably a water body. But resolution does vary a good deal. We're getting a lot of returns here, but not as many returns over here. So what we're trying to do is use interpolation to, one, reduce some of the redundancy in places where it's been sampled a lot, and two, fill in the areas that maybe haven't been sampled as well. So we're getting a regular sample. I'm going to focus on binning in this one. It's a kind of a simpler technique. And it often works just as well, and in some cases better than triangulation. But both techniques are valid. There are good reasons why you might want to use triangulation, but that's kind of a more detailed lesson. So I would encourage you to sort of play around with that and see what kind of surfaces you get when you do it. But in this case, we'll just use binning. Now the cell assignment type, we've got a number of different ways to decide how we're going to create this raster. So keep in mind that as we are working here, we're going to be defining little squares, and each square is likely to have more than one point in it. It could have 0 points in it, but most of the time it's going to have at least one, and usually many more than one, depending on the resolution. Right? The bigger the resolution, if we draw 10 meter squares, then we're going to have a lot of points in that square. So the question is, how do we decide when we're making a raster what the value is of that square? So one is we could take an average of all of the pixels, or sorry, all of the points that are in that square, just add them all up and divide by however many points there were. We can use IDW, inverse distance weighting, to basically try to estimate the value of the center of that pixel based on the surrounding pixels. So that's an interpolation technique. We're going to sort of, so that would be one option. We can use the maximum value within that square. So you might have 10 points in there and you just choose the point that has the highest elevation. You might choose the point that has the lowest elevation, so the minimum. Or you could choose the point that has the nearest, that's the nearest value. Typically, average, maximum, minimum, and nearest are going to run pretty quickly. IDW will take a little bit longer because it's got more work to do. And any of these will produce a different kind of surface. So the reason that there are 5 options here is that you may very well have different reasons, things that you're looking for. In this case, I'm going to choose minimum. And the second major option here is the void fill method. So what this means is that sometimes you will come across places that don't have any points in them, grid cells in your raster that aren't going to have any points. So this is a little thin in here, and this is certainly thin in here. So the question is, what values do you want to use for these places where you don't have any points to choose from? So typically you can either do a linear type of interpolation. You can do simple, where you're just sort of taking the average of the surrounding one. You can leave it totally blank, which is none, or you can fill it in with natural neighbor. So that's the one that I would encourage you to use most of the time, but again, there are good reasons to use other things depending on what you're doing. And that's kind of a focus for a more detailed class on LiDAR. Now the output data type is pretty key. So you've got 2 options here. So one is a float, so decimal values, and one is an int. So the question is, do you want to round this to your nearest data unit? So in this case, feet. Or do you want decimal values? And typically, so it's the same sort of trade-off as you'll see in everything else. Int is going to take up less room on disk, but it's going to be less precise. There are some reasons why you might want to use an int, but most of the time you're likely going to want to use a float when you're working with LiDAR data. Now sampling type, this is essentially how we're going to be constructing the grid. So we can do it using observations, but what I'm going to do is specify a cell size. This is probably a little bit more typical. So what we're going to do is define the resolution of the output raster. And in this case, our sampling value is 10. So that is going to be 10 feet. So each pixel is going to be 10 feet, but that's editable. You can change this to whatever you want. Usually this is going to be a function of sort of your output requirements and how good or how dense your point cloud is. So usually you want to try to have at least 1 point per pixel, at least. Usually, maybe a couple more than that. 10 feet is going to definitely have enough points. What I want to do is we'll do a 5-foot raster. So this is a little bit worse than 1 meter, a little bit better than 2. So this is a pretty fairly detailed DTM. Usually you can get away with 1 meter. But remember that we're working in the state plane coordinate system, Illinois West, and so we're dealing with feet. Now you could go in and you could change that. You can reproject this data in the same way that you would do it with other data sets. And you can go into environments and you can set things like output coordinates and do transformations and all of that stuff. We're going to leave it alone for now. So we're going to be creating a DTM using state plane Illinois West in feet. Now, I want to make sure, so we had applied I'm going to hit cancel here. We'll fill that stuff back in here in a second. But one of the things that you want to be aware of is that when you're making your DTM, you're going to be making it according to the filter that you've got defined here. So if you want to make only a ground layer, then you make sure that only ground is checked. If you want to do it on everything, then you make sure that all classes is checked. And we didn't talk about this much, but you can also distinguish between first returns, last returns, all of that stuff. But we're going to just do ground layer, so we're making a DTM, so that's what we had before. Here's our LAS dataset to raster, same input. And we'll call this Nachusa 5-foot, and we'll DTM.tiff. Slight change in the name there. The binning, we said we're going to use the minimum. So what the minimum value was, and we're going to use natural neighbor float, cell size, and a sampling value of 5. We didn't talk about the Z factor, but here if you're doing things like going from feet to meters, you're going to need to sort of specify Z factor that's going to do that conversion for you. We're going to leave everything in feet for now, keep it simple. So we'll hit OK. Now, some of these methods of creating DEMs are relatively fast. You can see that we took how many millions of points, 20-some million points, right? 2.3 million points, and we turned it into a 5-foot resolution DTM, and it only took a second. So, you know, these techniques can actually be relatively fast. Now, at the moment, we've got all of that stuff overlaid. All of our original LiDAR data is overlaid on top of the DTM. But if we uncheck this, then we get something that looks a little bit more typical, right? This looks a little bit more like a standard elevation model. You can see that we've got. I'm going to choose a visualization here that looks a little bit better. So we'll use a kind of a semi-standard. Here we go. Oops, don't want to do that. Okay, so we can change some of this around. We can do things like use a hill shade effect here to add a little bit of detail. And we can go in and modify our histogram. Actually, this looks pretty good. A lot of times you're going to get situations where you might get a stray return here or there. Maybe there's a lot of variation, but you can, in ways that we've sort of described in other lectures, you can sort of fiddle with that histogram and get a better representation. So this is essentially our DTM model. We can go in, zoom in a little bit. Obviously, this looks like mountain peaks, but it's all relative. We can zoom in here. One thing you'll notice is that we've got some very interesting sort of artifacting going on here around the edges. So this looks worse than it is because of the hill shade. So if we turn that off, you'll see a lot of that go away. We'll leave it on for now. But you can use your information tool, and we can recover values for things. So we're getting values of 6.96.5 feet, and you can see that it's quite detailed. So standard sort of float values. And if we turn our point data back on, this will be a good chance to sort of see how this worked out. So you can see the squares relatively clearly, and so in some cases, here and here we had 2 points. In this grid we had 3 in this one, 2 in this one. But if we look carefully, we should be able to find a couple of grid cells that have no points in them. Here's one over here. So this one just happened to not have a grid point in it, and so as a result, we just had to estimate that one. Okay, so let's zoom out and take one last look at this here. All right, so here we have overlaid our original 24 LAS data sets on top of our calculated DTM. Hope you learned something, and it's a pretty easy way. One of the advantages of doing this kind of work in Arc is that it is relatively easy on the resources. So LiDAR data sets can be difficult to kind of work through. They tend to be rather large. You saw that some of them, we're talking about tens of gigabytes for counties, so pretty big data sets. So Arc does a pretty good job of sort of handling that. So as you're working through this, I would encourage you to look at both of those options. Whenever the key here is the LAS data set. Lots of options that you can choose in terms of binning, triangulation, how big your output is. So I would encourage you to sort of play around with those different settings and just sort of see how it works. Okay, thanks for listening, and we'll catch you next time.